Bueno, bueno.
Hola Carlos, ¿cómo estáis?
¿Y tú?
Bien, bien. Comiendo unas galletitas antes de la
¿Oh?
clase. Comiendo galletas.
Ah,
Hoy si quiero no está muy tarde anoche.
eh, no, un poco más nomás. Pero nos faltaron algunas nomás de la tarea.
¿Cómo cuál?
A ver, déjame cachar. Eran como las preguntas sobre las preguntas que nos hacían. Con esas preguntas al final. Se
Ah,
comente
ya.
su resultado.
Ya.
Em, mm,
Sí, eso también me falta.
Ponte tú en la uno. Lo que nos pasó que no sabíamos si había que hacer la temperatura constante desde el principio.
¿Sí?
Eso no cachamos al final, en la
Ah.
última. ¿Qué pasa?
Igual lo que me di cuenta es que para las primeras partes, o sea, la A, la B, la C, como que eso no afecta mucho, en verdad.
Claro.
Como que
Pero
sería como
hasta ese
ponerle.
punto la temperatura todavía es constante.
O sea, y podría ser, puede ser que varíe, pero sería solo ponerle dependencia de tiempo, ¿no? Nada más, como que no cambia ningún cálculo, creo.
Mm.
Eh, Pero sí, no sé, igual me confunde un poco eso.
Quizás en la última parte nomás donde hay que asumir que la temperatura cambia. Es que dice el gas enfriado, tiene que cambiar.
Sí, pues, sí, el T-Cooling. Hola, hola.
Mm. Y la última, la 3. Tampoco cacho muy bien cómo podría variar la frecuencia con la posición
Con la posición.
Mm,
¿Qué pedía eso?
dentro de la esfera. ¿Es la 3 la
Ah,
última?
ah, verdad, quizá no la he escrito todavía.
Mm.
Ahora después de la clase voy a intentar terminarla.
Sí, igual. Hay que hacerlo.
Hay que hacerlo.
No queda otra.
Entonces la prueba sería la próxima semana, ¿no es cierto?
¿Verdad? Creo que le vamos a decir que el viernes de la próxima semana.
Bueno,
Mm.
bueno, acá
Ay, qué
nosotros
nervios.
tenemos astroquímica el jueves,
Oh.
que en verdad estudia re poco. Y en astroquímica no hemos tenido ninguna tarea ni nada, entonces tampoco sé cómo, qué tipo de ejercicio nos van a hacer.
Mm.
Hola.
Hola.
Hola, profe.
Hello.
Okay. Okay, so where did we stop? So we were here talking about synchrotron radiation, and I just wanted to sort of, we talked about the sort of simple version of this, and basically we had derived the perpendicular and parallel power as a function of solid angle, and had our fun with these constants, which we didn't really know, with the functional form, which we didn't really know, and so forth. And kind of had argued in a very hand-wavy sense that the power should go as the frequency to some spectral index, where this spectral index was related way back when to the spectral index of the distribution of energies of the electrons. Right? So there was some relation between the energy of the electrons and the distribution of that and what the ultimate spectrum coming out would look like. Sorry, my wife is making a tremendous amount of noise. Hopefully you can't hear that too much. I'm shaming her into making less noise. Okay, so the final thing here was mainly the two issues which you should remember. So you have this electron whipping around, and as it has speed close to the speed of light, the radiation is going to be beamed in some cone with a solid angle, or with an opening angle of roughly 1/gamma. So the Lorentz factor. And the width of the radiation pulse should basically become smaller as the energy increases. So as the energy increases, the cone will narrow, and we'll see it for a smaller amount of time around its cycle, right? The other thing is that the pulse is going to be shortened or foreshortened, meaning the photon emitted at the end of the pulse will almost catch up with the photon from the start. And so we will have, so as this thing is going around very, very fast, we will have that one pulse will start to kind of come up against the other pulse, and we'll have a train of these pulses. Right, so it'll look something like this. So those were the only two major points to sort of that I missed on last Wednesday. Okay, so with that in mind, we can now look at this in more detail. And so we will recall the Leinert-Weikart potentials, and we're going to now use them in relation to synchrotron radiation as opposed to Bremsstrahlung, thermal Bremsstrahlung. And so here we have the intensities of the EM fields as computed by these potentials, and we're basically going to look, in observer's coordinates and time. And so we have our, let's see, I can never remember. So this is the current potential, and this is the charge potential, right? And so we have just Q over R, and this extra factor here, which is our relativistic factor, essentially. So it's this quantity here, which is 1 minus this dot product, where n is the normal, the unit normal. So we have our conversions of time, which looks like this, or sort of multiplied out, looks like this. Right? And so we want to evaluate these things at some retarded time. And then we also might want to evaluate at some arrival time, which is slightly different. I guess that is basically the retarded time. So we have a geometry. So this thing is circling around. There's a B field in this direction. So the velocity is going like this. And at some instant, we have this situation. The velocity is going in this direction. The acceleration is going in this direction. And we want to measure the potential out here. And so recall that we had a gyration, it wasn't the gyration frequency because that's WG. This was the synchrotron frequency, I guess. I can't remember what it's called now. I should look it up just so I can be sure here. So it was, where was it? It was way up here. Okay, yeah, this was the cyclotron orbital frequency, okay, or the synchrotron orbital frequency, and it's related to the gyro frequency. All right, so we have that's equals this, and we can also rewrite this as just the energy of the electron. So we can then rewrite R here as basically a component of this, a component of this, and a component of this. We can write the n vector here as 0, this, and this. This is x, y, z, and x, y, z. And so the dot product of these things should give us this thing. And so then when we plug this in, we end up with this thing here should look like this. Or rather, we're moving this thing on one side and moving this on the other side. And so this now becomes this, so we should have something which looks like that. Okay. So that's our situation. And what we want to do is then look at the magnetic potential. And so the magnetic potential, which we had here before, right, and we were looking at it like this, we're going to plug in this thing here and understand what these things are. Actually, here's our potential. So we want the magnetic version of this. So we have here our K, we have here our R, which is now in terms of a retarded time. So it's now been delayed, and we have our velocity. And so this can be approximated if we do this out. We can assume that this is going to be large with respect to this. And so we can move outside of this. And so we end up with something which looks roughly like that. And these things are now in the initial frame. And so we also have that our radius as a function of this initial frame time will be the trajectory of the electron around the magnetic field. And this big R is the distance to the observer. Right, so this is the little r, this is the big one. So we want to again evaluate this thing. And so we can notice that this thing should be equal to this difference, the differential of the time in R frame to the time in the prime frame. This is the relativistic factor. And so this component here will end up being this thing. So it's, in essence, it's the time derivative of this thing. And so we have a cosine factor of theta here, which comes from this. We have our frequency because it's oscillating around. And then we have our V divided by C, which we can rewrite as this thing. So this thing will become very small when either of these factors, or when all of these factors approach unity. All right, so when this cosine is very close to 0, when this is perfectly aligned along our line of sight, and then when this thing is very, very large, right? So in those cases, 1 minus 1 then will be 0. So this, of course, is an ultra-relativistic case where this thing becomes close to 1. And so in the ultra-relativistic case, we can make some assumptions. So beta, which is equal to this, is approximately, we can do an expansion, and it's approximately equal to this. Cosine theta, in this case, can be expanded to be this. And then this thing can be expanded to be this. And we can then multiply all these together, and we end up with this kappa factor is proportional to this. In this small angle, small or perfectly aligned time, and high Lorentz factor. So we can do a similar expansion for our retarded time. And so this thing will end up becoming this ugly thing. And so we have a factor of gamma squared, 1 over gamma squared here. We have theta squared, which are just these two factors here. And then we have our cyclotron frequency. And again, it's sort of related to these factors. We can define some particular time here, which is this particular time is a function of gamma and a function of theta, but this sort of, trying to remember what the term for it is, but it will be kind of the peak time when this sort of happens. So if I have this is when you basically have an inflection point here, which happens at this particular time. So this particular time is related to these three variables like this. Okay, so we have these times are related. So this is the t-axis and the t-prime axis, and basically we have that these times will be roughly equal at this t star value, but otherwise they won't be. And so what happens is, as this thing is in its process of moving, you have some time 0 where they're equal, and then you have some other time here, and there's a portion where it's proportional, and then at some point it becomes not proportional, so it becomes proportional to t to the 1/3. And this again just comes from the monster here. So if we look at how these are related, so this t and this t, obviously if they're, let's see, if they're close to 0, yeah, this whole thing is 0, this whole thing is 0, and we also have that r must be equal to 0. And then if we evaluate these out, they should go as basically you have a t here, a t squared here, and a t. And so depending on what these values are, this thing will be t to the 3rd. Or if these things are relatively large, this will drop off and it will be t to the 1. Right? And so this is how we get these regimes here. Right? So for t prime much less than this, we have that they're related as a function of t prime. And for t prime much larger than this, we have that they're related as t to the t3rd. Uh-oh, we lost someone. So if we have theta equals 0, or we have theta is much smaller than 1 over gamma, this t star should roughly equal the critical frequency. And we could also label it as 1 over omega star. Basically, the star is just the inflection point where these two regimes come together. So if we then plug this all back into our potential, we have a potential that's going in the x direction, which looks like this. So it has the sort of normal things here, but then there's this extra factor of omega b times t prime and another factor here, which is related to gamma minus 2, theta squared, and then omega squared t prime squared. And this is what the potential will look like in the x component. And so if we plot that, it should look like this. And so we should have a peak at some point, which is T star. And so before that peak, this potential will go as T, and after this peak, the potential will go as T to the -3, or 1/3, rather. And we'll have a peak, which is maximized here. So we have, this is our equation for our potential. We can substitute in our Vx equals this, and we have our time different, or our time conversion between these two for the retarded time. And so again, we have two regimes here, right? Which is just what I said here, where we have either the potential is going as T, or it's going as T the -1/3. And we have this peak. Okay, so what does this actually mean? So what happens is we can end up looking at the magnetic field and look at the magnetic field pulse profile as a function of time. And so here, the magnetic field is going to be the curl of A. And so the Z component of the magnetic field will be proportional to the time derivative of the X component of the potential following this. And so because we had something which went like this and had a nice time variance here, we're going to see an interesting sort of component. Actually, is this the Z direction or the X direction? I think I might have gotten this wrong. Yeah, that should be X. There we go. The old plot was not so pretty. Okay, so right, so that works now. Right, so this is BZ, not so pretty, and this is the functional form. So we have, in essence, a peak in the magnetic field, which has a sort of characteristic time scale, which is given by this T star, and so it'll peak up. It also has a dip here and a dip here. And so this BZ, plugging in what we had for a X here, will be these factors times this quantity or this quantity, depending on which time scale we're at. And so what's interesting here is that this actually doesn't have a time dependence. The time dependence falls out here because it's just going as T, and we take the time derivative, so T falls out. Whereas this thing has a time dependence, which goes as T to the -4/3. And this characteristic sort of frequency in the spectrum for this single pulse with some Lorentz factor gamma viewed from some angle theta along, towards our line of sight, out of the orbital plane will be given by this frequency star here, which is 1/T star, and that is roughly equal to this. And so what's sort of interesting here is that there are no features in the potential or the field on scales smaller than this. It's just a pulse. And the power falls rapidly for frequencies which are much larger than this, right? So it basically goes to 0 very quickly. And so again, we can see that we have a pulse which is happening in the perpendicular direction to our motion, right? The motion's going in the X direction. So we have something which appears to be akin to an electromagnetic wave, at least in this magnetic field pulse. Now this is, of course, when we do the transform, we end up having something which was a magnetic pulse in one direction or in one plane. When we transform it, it's going to have both a component of magnetic field and electric field. And so it will, again, appear like radiation, very similar to what happened with the the Coulomb field in the Bremsstrahlung case. Is everyone with me so far?
I have a question here, specifically in that plot, because I don't understand very well if in the first term for times lesser than well, this time, that is not a time dependent, but why in I don't know, I can't see.
Why does it have a pulse here?
Yes, why it's not a constant or?
It's mostly that you could almost think it should actually be more like a square, but it's not quite. The thing is, like, so as this thing, it's not going to perfectly go from this regime to this regime, and so we won't see it perfectly. We have to have them meet, and so this is them meeting. It should be sort of more squared off, I would think, but it's mostly, again, this is a little bit hand wavy in how we're treating this in terms of just two regimes. And so in meeting these two regimes, it's not like it's magically this up to here and then it's magically this up to here, right? It's going to be it's going to be sort of smoothed out a little bit. And so I think that's what's going on with this plot, is this is more intrinsically true of the functional form with time, whereas this is the extreme. Remember, this is t much less than this, right? So it's way in here. So it's only, we're talking about this.
Okay. Thank you.
Yeah. But I understand your point. Yeah, we're actually fully not to the, this is in detail, this is not in gory detail. And so we will come back in very excruciating detail in a second. But yeah, the idea of this is again, just to look at the sort of functional form. Other questions? Okay. So despite the fact that there's very little power here, it's still potentially of low interest because this is what dominates the low frequency end of the power spectrum. So the low frequency power end is dominated by the wings of the pulse. And so this thing in the sort of high frequency end of the high time range will go like this. And so this thing, if we want to sort of approximate it, we could, if this thing is large, then this thing will drop off compared to this angle, and we'll end up with something which is approximately equal to this. So if we do a Fourier transform of this thing to get the frequency dependence, we will plug in and do our Fourier transform, and we end up with a frequency dependence as a function of angle, which will have this form. So it goes as omega to the 1/3 divided by our cyclotron characteristic frequency. And remember, this is for frequencies much or less than this characteristic frequency. Right, so adopted, this is basically is just, this thing will end up being this, because this time dependence of -4/3 in this form will give us something which looks like that. And so our power spectrum, which is going to be the square of this magnetic field, is going to go as omega to the 2/3 plus some constants here. And so this is basically true for an observer at a specific angle relative to the orbital plane. And of course, we want to integrate that over this distribution over all possible angles. And so here, what we want to do is think about the total energy emitted by a single gyration that we're going to obtain integrating the Poynting flux. And so we're going to integrate over all angles, integrate over all time, and that's going to give us the total amount of work being done or energy emitted. And so we have here our energy density and magnetic field, right? So just b squared divided by 4 pi and then multiplied by c. So we do this integral, and we can equate this thing, we can Fourier transform this into a frequency and do the same thing integrating over the frequency and integrating over the solid angle. So those should be relatively synonymous. Okay, so what do we actually then do here? So we have to remember that this frequency here acts as a cutoff. And so what this means is that if we observe over the entire frequency, there's some frequency beyond which we will see all the power drop out. And so if we look at the frequency dependence, we have this thing, and we can think of this as being equal to this sort of maximized at some angle. So basically what this means is, so if we have some cutoff frequency, this cutoff frequency is dependent on the Lorentz factor and this theta. And so in this sense, the cutoff frequency is dependent on our angle from which we look with respect to this thing moving around. And so there's going to be some frequency here where the observer will see the radiation only if this angle is less than some maximum angle. And so we can set that angle as being the frequency at this angle equals this cutoff frequency. And so for frequencies much less than this, what this means is that we have a frequency, or we have an angle, which is frequency dependent. And it depends on this. This was the point of doing this exercise before, right? So this particular thing, if we invert it, we get a frequency. And so we can relate the angle to this frequency relative to this characteristic frequency. So we can then think about this magnetic field coming out at a certain frequency, and roughly speaking, we could approximate that by this theta max times this magnetic field squared. And this magnetic field is, again, this thing here. Of course, this thing is equal to the opposite of this thing. And so, let's see, is that right? Did I do that right? No. Okay, yeah, all right. Roughly speaking, this maximum thing is going to be equal to this. And we can kind of see this by thinking about this integral. And if we do this particular thing, we have this dependence, we square it, and this maximum here will be times this frequency dependence. And so this thing will have some constant times this. And that's where this sort of comes from. So the B field squared is roughly equal to this, and this thing ends up roughly being equal to that. You can kind of make that that equivalence. So all in all, we have we can approximate this thing as being equal to this, and we want to take the integral over this frequency. And so we can also plug in this thing here and divide out some of the constants. And what we end up with is that the total power here should be related to this characteristic frequency, or sorry, this cyclotron frequency times this work divided by 2 pi. That should be the total power that comes out. And so if we do this integral as a function of this power as a function of frequency, we should end up getting this, or this should be the normalization of it. This is basically coming from this equivalence here. Okay, so this has a functional form of this thing. And so roughly speaking, we can think of this critical frequency as being equal to gamma to the third times this. And this thing will then equal this, where this thing here has now been turned into energy units. So we have 1 energy here, we have 3 energies here, and so we end up with E squared on top. The result of this is primarily that we have a spectrum which goes like this, so it goes as 1/3, and then will fall off with an exponential, which goes as e to the minus x. And so we end up with the low frequency end, which we got from this portion, right? The low frequency end will be like this. And the high frequency end, because it goes as just the time, ends up having this stronger fall off. And so for frequencies lower than our nominal sort of frequency, and this should be nu, not v. Font. Okay, so this is the idea, is that we have the power coming out here will be sort of transformed into, there is a pulse, it has some pulse shape, and this will transform into some frequency dependence. And so we get that at low frequencies, and then we'll have a cutoff here. We'll have something else which happens, an inflection point at this point. And this is simply related, this is just going off of this portion, the low frequency portion of, or the long timescale portion of this pulse. And the exponential cutoff will come from the fact that we have a constant value here. And so this will give us a sort of finite level amount of energy, and so we can't really have much more than that, and so we'll end up having a cutoff there. Okay, so again, a little bit hand wavy, but hopefully we have an impression of how this spectrum should go. Now, this is for an individual electron, and we then want to understand what real synchrotron radiation would look like, and that's where we will need to take a distribution of electron velocities or energies or gammas and convolve this with this. And so typically over a short portion of a short range in energies, we will have a number density of electrons as a function of energy that over this small range in energy. And we can approximate this like a power law, right, which is what we did last time or previously. We can also note that this particular form is equivalent to this form. And so if we want to look at a distribution in a log interval of gamma, we can rewrite this as this. So we're taking the derivatives of these two things. And so we have basically a extra factor of gamma here. And we've, right, which we plugged in from this. So we now have dln gamma here. And we can note that this functional form looks like this times a gamma. And so we can rewrite this as gamma ny dln ny. So this just gives us a number in a given interval of log gamma. We can also remember that the power radiated by a single electron is proportional to this thing. So it's the energy density, so the magnetic field squared, our pitch angle squared, et cetera. And this is equal to gamma squared, or proportionally gamma squared. And we can also relate this to our frequency by this factor here. So we then can look at what the power coming out in a log interval of frequency is. And we can do a similar trick here where we look at this power per log frequency it's going to be related to the power times the number of electrons times our frequency times dl and w. And this, again, is just doing a similar trick here. This thing we can turn into gamma based on this. And so we can plug in this, and this with the proportionality, so we lose the constants such as WG here. And we can note now that plugging in the dependence on gamma squared, the dependence here, which comes from this thing, we end up having something which looks like this. Or we could again fold it back and get a frequency dependence, which looks like this. And so the extra 2, 3 rather than 1 comes from 2 here and 1 here, right? And then this frequency dependence is just, this is square root. So we have this extra 1/2 here. So we can then think about the functional form of the power coming out as being proportional to omega to some factor here, some index, spectral index. And the spectral index will take the form of b minus 1/2, which is close to this, right? But it's because this is a differential form. Once we sort of integrate it here, we will have an extra. Well, that's where this extra 1 comes from, or I guess, yeah. And so we will end up having a frequency dependence which goes like this. Okay, everyone with me? Hopefully. Okay. So we now want to again do this trick of okay, let's actually divide this out and look at the parallel and the perpendicular components and really understand the system in more detail. And so we're going to revisit this scenario now, dividing things into this sort of schema where we now have a mixed X, Y, and Z direction. We don't have some preference on X and some very specific geometry. So we now have a situation here where the unit vector is going in this direction. We have some velocity, which is out here. There's an acceleration, and we have some curvature here. And so what we want to do now, we have a line of sight, which is now theta here. And we can divide this into unit vectors in the perpendicular and the parallel direction. And we then also can estimate what this curvature radius is, which is related to the velocity times the time in the electron frame divided by this curvature, this radius here. So we revisit this formula, which is the change in work as a function of frequency, as a function of solid angle, or over an infinitesimal frequency and infinitesimal solid angle. This thing is going to be equal to our charge, our frequency squared, and some constants, and then the integral of this absolute value of the square of the integral of this thing, which is our sort of the cross product of with n and our velocity, and then the magnetic field vector here cross product with that. So this is quite a lot. This thing is the unit vector in the y-axis for some symmetry. This thing is n crossed with this. We have here the absolute value of beta here is close to 1, so we're in the relativistic regime, and so this applies as well. So this thing, plugging in these will end up being equal to our unit vector times the sine of this angle here. This being the value of that angle. And then our parallel component will be the cosine of that angle, and then sine of this theta here. We can get a delayed time And so the delayed time will be this t prime minus our unit vector here, dot product with r, and r is this, let's see, yeah, r0 is, I'm blanking on it. Not showing this. It should be, I believe it should be the full distance to us as a function of time. No, okay, r is this thing. Yeah, so it's the change, sorry. It's the little r here. We go way back. It's this little r. So it's the, here we go. All right, so it's the dot product of this with this little r, so this thing. So we can plug in what this thing should be. And so this radius, which has a vector now, it will be related to, and it's this thing here, this radius of curvature will be related to the sine of this angle, the cosine of that, and then our radius of curvature, length here, A divided by C. Okay. So this approximately should be equal to this ugly thing when we expand out these sort of cosine and sine theta terms. So we have various dependencies on gamma everywhere from this. And so this function of time will be a strong function of various gammas and theta, which is again what we had said before, but now this is sort of the full-blown functional form of it. And so we can divide this work into a parallel and a perpendicular component. And so we then will sort of divide this thing up into its perpendicular and parallel components. And we end up with a functional form which looks like this. So we're taking this integral, plugging in this thing here for t prime, which is here, plugging in actually t prime minus this thing, right? And then plugging in this or this for this particular portion, right? And so we have a lot of strong dependencies on gamma in various places, some functionality on theta as well. So this is not a pretty integral by any means. Note that to simplify this equation, we've taken this thing to equal this. So it's not exactly theta squared, but it's this quantity here. Okay. So making a couple of variable changes makes this slightly prettier, although not much. And so we can end up having that we couple all of these constants into a value y, and we couple all of these constants, the frequency dependence, into this value eta. So we had frequency dependence here, we have frequency dependence here, here, etc. And then we have the time dependence here. Right, so the time dependence here, 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 and here. So what this ends up doing inside this integral is you now have an integral which looks a little bit cleaner. It still has an imaginary component to it, right? It's an exponential of this thing. And so these are not trivial integrals to deal with. And so we need to integrate these over all frequencies, which in this case, sorry, all time. And so in this case, the time is negative infinity to positive infinity. And we want to know that most of the radiation is going to come out at angles close to 0. if we're in the relativistic case. So if we have strong beaming, it's mostly going to come out in this direction, right? So we can simplify this thing under the assumption that theta equals 0. This thing will end up just having a very weak, well, not a weak frequency dependence, but just the frequency dependence divided by the critical frequency. So it turns out most of these constants reduce to this critical frequency, or can be rewritten in terms of that. Recalling that our radius of curvature is equal to this, and our frequency is equal to this. And so actually the gammas fall out, and everything, basically all the gammas are held in this thing here. Okay, so that helps us a little bit. And so once we reduce this to this dependence, this is just now a frequency dependent. So omega, and then we have some constants here. And then this is all our time dependence here. This will, in essence, give us a frequency dependence which depends on this only through this factor here, omega divided by omega c. And we have some angular dependence which comes in only through this thing here, the combination of gamma and theta. And these integrals turn out to be very similar to modified Bessel functions. Well, actually, once we've rewritten them in this way and sort of simplify this, we can pull out that these are modified Bessel functions. And so these end up having relatively simple, in quotes, sort of functional forms. So all of this integral here then becomes this thing. And so this is a modified Bessel function squared, and it's a modified Bessel function to the 2/3 order. And likewise, this is a modified Bessel function squared to the 1/3 order as a function of this thing. Okay, and then we have dependencies on this, whoops, which is related to this, and on our frequency here, squared. We then can also think about the fact that this thing is orbiting around, and there's a solid angle over which the radiation is going to come out. So we have the magnetic field going this way, we have this thing going around, and the radiation is going to come out in this direction, and so we can integrate over this thing here. And so the radiation is going to come out in a cone which has this angle is going to be related to the pitch. Well, basically this angle here is 1 over gamma, and this we can relate to the pitch angle, which we'll say it has a half angle alpha. And so we want to take this solid angle here. And so this solid angle for individual shells will be related to d theta. So this is some d theta here, sine theta, or sine alpha, right? And then 2 pi to get the whole thing here. So we then have a sort of frequency dependence where we're trying to integrate over the solid angle. So to integrate over this thing. So we have our variables that come out, and we have only this dependence on theta gamma, or, yeah, the 1 plus theta gamma squared here. And then likewise, we have a similar function here. So we can reduce these further by moving some of these variables out and considering that we make, again, a variable substitution where we look at x is this frequency dependence divided by this critical frequency. So it's very close to eta, but for, in particular, eta with theta close to 0. And so we end up having, we can rewrite this thing or this integral as these things. And these things are the integrals of these modified Bessel functions, or rather, this is the integral of a modified Bessel function. This is the modified Bessel function. And so the perpendicular and the parallel case are this combination of these two factors. This is not pretty at all. And I'm glossing over a lot of the math. There are pages of equations you can go through if you really want to. I don't necessarily think that's so useful, other than to understand sort of where this comes from. So this thing, we can then convert this. So this is now the power coming out in the perpendicular and the parallel directions as a function of frequency. And so we can look at this. This is just turns into these guys. And so we now have this sort of stuff here. We have this integral, and we have this extra x factor. We have to turn it back into a functional form of frequency. So we have our constants out here and these guys, and our constants out here and these guys. Noting that basically we want to convert this emitted power into a frequency, all we have to do is divide by the orbital period of a charge, which should be roughly this. And so if we divide by that, we end up dividing this out and we end up getting this. The magnetic field comes from in here. Right? And then the gamma factor is then lost in here. Okay. So we can again, if we merge these two and get the total power that's coming out, magically these have the same units, and fx plus fx is 2fx, g minus g, you lose it. And so you end up having something which looks like this. And this thing has a functional form which looks like this. As a function of x, which is omega divided by omega critical here. And so at very, very low x, so x much less than 1, it has a functional form which goes like this. So again, we recovered this frequency dependence to the 1/3, right? And in fact, it was, rather than, it just has an extra 2 here, but it's more or less the omega divided by omega c to the 1/3 power, which is what we had derived in the start of this up here, right? So we had come back and said, okay, where is this? Yeah, this work has to be sort of avoided this power. Oops, I skipped a couple things. Okay, and then far away, it ends up having this functional form. And so we hadn't derived this before. We had only derived this in a hand-wavy fashion. But basically at very high x, you see that this has a strong fall off here. And this fall off goes as e to the minus x times x to the 1/2. And so here is our exponential fall off. And roughly speaking, you can approximate this by this equation here. And this has a peak at a frequency omega, which is about 0.3 times this critical frequency. And this value here should be roughly equal to 0.9 in these sort of normalized units. This functional form is sort of normalized. So plugging that back in, you could end up getting the power out. Right? It's just going to go as this frequency form. Okay. There are some useful integrals you can do. So this thing here, so x to the mu times fx dx, integrating this. So this would be integrating over the basically doing this integral here, which is what we need to do here. Generally speaking, this thing here, if we were to integrate it, looks like this. And integrating G here ends up looking like this. These are gamma functions. And again, they're not very pretty either. But you can do this. And you'll see sort of why we need to do this in a second. So we have a functional form where this thing is some constants times the B field, oops, come on, times x to some power times e to the minus x, or this thing. So this thing here, the total power coming out, we can end up showing that this thing ends up looking like this when we multiply everything out. And what's sort of interesting is that so this was for what is it, one particular electron. And so when we want to think about things in terms of a spectrum of electrons, and we want to then multiply, to end up doing this sort of thing, right? So we have some distribution which looks like this, which has some power law. And so this is the power from an individual electron. And we then want to have a distribution which will go as some factor of gamma or some factor of omega or some factor of x, right? We then have to use these, whoops, where is it? These integral forms. So this is now thinking about the distribution for a distribution of electrons with some range of a spectrum, which is given by a slope p or minus p. We can derive the total power coming out from this ensemble of electrons. And this thing will look like this, following this sort of nomenclature. So we have dependence on magnetic field. We have a dependence on magnetic field here which has a spectral dependence depending on the electron spectrum. We have a frequency dependence, which depends on this. And then we have a bunch of constants, gamma functions, which depend on the spectral index of the electron distribution. And then an extra factor here. Typically what is done, because we don't necessarily know all of this, we rewrite this simply as this. And so if the value of P is more or less constant over some frequency interval, which is a decent sort of representation, and we assume some sort of isotropic symmetry, so the electrons are distributed not uniformly in velocity, but are random with respect to a uniform magnetic field, then we can couple all of these things into a constant times the magnetic dependence, the magnetic field dependence, and the frequency dependence. And so these constants, which are a function of P, right? There's P's all over the place. They come in here, but that's just the normalization. And so typically, if you were to go out and measure a spectrum in 2 points and get a slope, if that was from synchrotron, right, you know the frequencies that you measured it at, you also know the slope, and so you can then measure the total power coming out, and that total power over that frequency range will, with this frequency dependence, will give you this, right? And so there's a magnetic field dependence and some constants, which depend only on the spectrum, the spectral slope, which you know. So you could go in and plug those in, and you make some assumption for the pitch angle, which should be averaged over, and you then can derive the magnetic field. So you measure the spectral slope, the energy of that coming out, and all of a sudden you can get the magnetic field that was needed to produce that. Modulo the fact that you mean, there also is some dependence intrinsic in here on gamma, on the electron speeds. But that actually comes through in this P. So the distribution of, oops, where is it? Here, right? So this P is the shape of the intrinsic distribution of electron speeds. And so the P is related to gamma. Okay, so we took what is a very gory, detailed problem and kind of simplified it into this. And so if you have to remember anything, it's this right here. The observed spectrum is going to depend on the magnetic field and the normalization for the electrons. And of course, the slope. Okay. So this sort of, the shape of this frequency, or the shape of the frequency distribution here will be determined by the properties of the synchrotron emission and the energy distribution of the emitting particles. And so in a simple case, you have a uniform distribution or power law declining distribution of electrons. So what you do is you go out and you measure some power, and the power is a functional form of the frequency to minus s. And this will be due to an electron distribution, which has a functional form where the energy goes as minus p. And just what I said. A single particle spectrum will have this dependence, right? And this critical frequency. And so this isotropic energy coming out will be related to the number of particles, the spectrum of each individual particle, and then integrating over the energies. And so this thing will be equal roughly to this. This is the total energy coming out. And so it'll look something like this as a function of frequency. And so this is the superposition of individual electrons, where each individual electron has, where did it go? This spectrum, right? But when you have this particular form is dependent on E. And so, well, actually E squared. And so this thing, if you have a distribution of energies, you have a distribution of peaks. And so in superposition, you will end up seeing something which looks like that. The number of particles with a certain energy decreases, it depends on P, but may have something where you have fewer particles of higher energy than lower energy. And so you will end up with a composite spectrum which looks like this. And again, this is just a power law superposition. And so we have something which looks like this, which ends up looking like this. Okay. In real life, you might see something which looks like this. This is one of the brightest radio sources in the sky, 3C273. And you can see that it has a nice power law spectrum here. Then this is the optical regime. So it's got a black body emission from something else. But this power law in the radio ends up being from synchrotron, from a jet. And it dominates below the sort of optical band for this particular object, right? And so measuring this, you can then understand what is the distribution of electron energies. And of course, this extends all the way back to the radio. But you can figure out that, because we see it all the way up to the optical frequencies, and even maybe even the X-rays or the UV, once we subtract this off, this requires electrons which are almost going the speed of light, right? And so there's something which is injecting energy very, very rapidly, which turns out to be a radio jet. Okay, so Another thing we can sort of do is estimate what the total amount of energy is coming related to the electrons that are giving rise to synchrotron radiation. So there are many different types of sources. So they could be synchrotron sources in our galactic disk or supernova remnants. And basically, it's kind of expected that there should, and after a while, there will be an equipartition between the relativistic particles and the magnetic field. It doesn't have to be the case, but if you give it long enough, then you would expect them to kind of come into some sort of equipartition. Why? And so this is, basically large magnetic fields will lead to the acceleration of relativistic electrons. At the same time, large particle energies will be able to produce and generate magnetic fields. And so if one of them gets too strong, what's going to happen is you're going to damp the other one out, or you're going to boost the other one up. So you always will have them, they should tend towards equipartition. Or at least that's the argument that people give. And so if we have some source, which we measure its luminosity, we can associate that source with having a minimum total energy. And we can also associate that energy with being near equipartition, or potentially being near equipartition. We can say, what if it is? If one assumes an equipartition value, then the observed luminosity will give you a total energy of the system, the total magnetic energy plus the total particle energy, because they're in equipartition, right? So it's more or less half of the total. And so we can consider the following example. So we have a supernova remnant. It has some value. It's going to contain a mixture of magnetic fields and cosmic rays. And so we can estimate the magnetic field energy density as just this. And we can also estimate the total power coming out from synchrotron radiation, which should be this. So it's just the magnetic field to this power and some sort of constant here. And this will be the energy density coming out from electrons. And so under equipartition, you have the total energy is going to be equal to this electron energy density plus the magnetic field energy density, or the magnetic field energy density and the cosmic ray energy density. And this is just the radiation coming from synchrotron. And we don't necessarily know the total energy from the cosmic rays. We only know it from the synchrotron radiation that we see, where we're inferring something about the population. And so that's why we typically use a factor of 1 plus k here for this to relate this to this. And typically k is around 40. And so if you assume that the total energy is related to this, if you assume equipartition, then this energy is related to b squared plus p to the minus p plus 1. And so in essence, depending on what p is, if p is not too much, the minimum energy you would have should end up being this combination. So it should end up being roughly 2u from the cosmic ray or 2u from the magnetic field. And so what this will look like is this. So you have the energy, the magnetic field, and the cosmic ray energy goes like this. So minus p plus 1, and so it increases as a function of magnetic field. Then, let's say it decreases as a function of magnetic field. So it's this dashed line. So if the magnetic field is higher, this thing is negative. If p is positive, this thing is going down. And then the energy density from the magnetic field is going as b squared, so it goes up. And so typically you will have an energy from the two, which looks like this, and they should meet somewhere in the middle here if you have equipartition. And so you can always calculate this value, and you can measure this, you can assume this, and therefore you can assume that maybe this system is in equipartition, and therefore you can get a constraint on the magnetic field simply from the energetics as well. So we can then compare this to other ways of measuring the magnetic field and see if this works. And in general, it kind of does. Plugging this in its full-blown glory, you can end up as estimating the magnetic field. And this is the functional form of this, plugging in all of this loveliness here into this assumption. But you can end up with some functional forms. This is the flux of the source at some frequency. This is the spectral dependence, right? So the slope. This is Z here is the redshift. This is the difference between the two different bands. Here's our K factor here. Then we have a couple of other things here. So this is the size of the region, if you can resolve it. This is S is the length, or the length of the source along the line of sight, so how big it is in the line of sight. And so this gives you roughly the volume. And then this thing is the angle of the magnetic field with respect to our line of sight. And you could just average over it if you wanted to. But you could also assume a uniform magnetic field as well. And this will give you an estimate of the magnetic field. So you can go and you can measure sources at some frequency. You can, if you resolve them, say with VLBA, you can estimate their size, and therefore you can estimate what the minimum magnetic field should be for that source under this assumption of equipartition. It doesn't have to be, it could be larger. And so by this context, we can then estimate what the magnetic fields are for, say, radio jets or for the shocks of supernovae, right? So typically, at a minimum energy, the ratio of the cosmic particle energy to the field energy will roughly be this ratio here, and should roughly be 4/3. So it's nearly unity, not quite. And so this implies, or is basically somewhat circular, but this implies an equipartition of energy because of this sort of minimum energy ratio. And so they'll be nearly equal. We don't actually know if this exists, but we often assume it does just because it's kind of a reasonable assumption that if you have interacting components, they will tend to go towards an equipartition as opposed to going off into one direction, just because that requires much more energy. So it basically is a minimum energy assumption. One of the issues is that when people started measuring the radioluminosities of extragalactic radio sources, these large radio jets, there were huge energy requirements, even assuming this minimum energy. And so just to even get out of some of the problems that they had, if they had to require even more energy, then they would need a mechanism that had to even, to accelerate electrons or to generate magnetic fields to even stronger sort of degrees. And so this seemed like something reasonable just because the energy requirements were so huge. The benefit of this is it eliminates a free parameter, and it ends up permitting estimates of both the relativistic particle energies and the magnetic field strengths of radio sources. And if when you want to actually get numerical values of this, you have to plug in the particle energies and emission coefficients and things, but you can do it, and you can get out rough values of this, and you could plug in errors too and get out errors on this as well. Okay. Any questions?
Yes. What will happen if equipartition doesn't exist? Maybe we can talk about some anisotropy, or.
Well, so yeah, so the equipartition in this sense is an equipartition simply of energies. So it's an energy balance more than anything else. And so I guess there could be, yeah, you could talk about there being some sort of anisotropy, but this is already factoring in the relativistic corrections for the the overall integration of the spectrum and trying to understand it. So as long as you kind of understand the relativistic particle energies, right, to take out the beaming constraints, then yeah, you can estimate this, or you can use this to estimate what both the magnetic field and the relativistic energies are. If you go away from equipartition, so you require more energy, then you need a mechanism that will generate that, either from the magnetic field side or from the particle side. And so you can get that. There are cases where you might have something which is too young to have come into equipartition, right? Or you might have some sort of driving force which is driving it out of equipartition. But you need some extra input there in general to create that. If that makes sense. It doesn't really answer your question, I don't think, but it's just an assumption, and you can go outside of that assumption, but what it means is you have to have larger energies.
Thank you.
Yeah. Okay, I think we're nearing our time here. I just wanted one more thing before I go. And so we can make an estimate of the cooling time in the same way that we did before with the thermal protron, right? And so a typical synchrotron electron will have an energy, a relativistic energy, which will look like this. And the power emitted will look like this from a single electron. And so what we can do is estimate how quickly that electron will cool, right? And so it's just taking the energy and the radiation from that electron, the power that's coming out, and the time is just E divided by P. And so we can plug that in and we get a relation which is related to the gamma factor and the magnetic field. So a stronger magnetic field will cool faster, and a faster electron will cool faster. Right? Those are the dependencies, more or less. If we shift between the emitted and the observed frame, we also have to consider a relativistic boosting factor. And so this means that photons basically, if they have a frequency of nu, this was going to be blue shifted. And for a given electron, most of the energy is going to come out very close to the critical frequency, which is what we had shown with the spectrum initially. But this, of course, is boosted by this factor gamma. And so this synchrotron timescale, the observed one, will end up having an extra factor here, which is related to our Doppler shift. Oops, yes. I need to stop. And so the observed as a function of frequency, what this means if we turn everything into frequency and pull out the magnetic field here, we have our Doppler factor here, but we have a frequency dependence, which goes like this. And so what this is sort of indicating, right? We've turned this into, this is just the frequency divided by the critical frequency. So we get this out. And so even though this thing isn't implicitly in this thing, what it means is that the observed frequency is independent of the electron distribution to some extent. But there's this Doppler shift. And so provided there are enough electrons to yield, to actually have some electron with this energy or with this gamma, this time scale at a particular frequency will allow you to estimate sort of cooling time. What does it mean to have a frequency-dependent cooling time? So the spectrum is, related to the energies of the distribution of electrons. Right? And so we can estimate the synchrotron cooling time at a particular frequency, and that will tell us something about, if there's no curvature in the spectrum, we can know that those electrons were accelerated relatively rapidly in a relatively short time ago, because the cooling time as a function of frequency actually maps very closely to gamma, just because they're related by the gamma equals the frequency divided by frequency critical. And so you can just observe the spectrum, and this will give you an indication of how rapidly the process is by which electrons are being re-injected or re-accelerated in that particular system. So to give you an example, here are 3 radio sources, and you can see this CAS A has a spectrum which is very, very flat, right? The slope is power law for 1, 2, 3, almost 3 orders of magnitude, right? And Virgo A, same way. It has a slope which is pretty constant. And what it means is that these electrons here at the higher frequencies are having to be re-accelerated at a rate which is comparable to the synchrotron cooling time. If it wasn't, then we would see something which is like this, where the power coming out here would be less because they're being decelerated, right? They're losing energy and they're moving over here. And they're giving their power to lower frequencies. And so if you see curvature in the spectrum, like you do in sig A, what that means is that the electrons have had time to cool, right, via synchrotron. So the fastest electrons, which cool, they're going to cool the fastest. They lose energy the fastest, they're going to be down, and you get a pileup of electrons out here. And so you end up with this synchrotron curvature, or a spectral steepening. And this allows you to estimate how long ago this source might have been accelerated. And for instance, if you look in a jet, you might see something which looks like this. The jet is constantly re-accelerating the electrons as they're moving out. And then you might look at the lobe, where the jet no longer exists. There's no longer a mechanism for re-acceleration. And so those electrons will cool relatively rapidly, and they might have a spectrum which looks like this. And you can estimate, roughly speaking, when was their last re-acceleration, right? By comparing these 2 slopes. If you can measure the intrinsic slope here. So you could play games like this to kind of estimate how old a radio lobe was, how much energy was initially involved, and all the things about the radio jets that were, in order to understand what drives them. Okay, I'll stop here. We still have to deal with polarization and some other things, but I'll come back to that on Wednesday, okay? Any questions, thoughts? You guys are done.
Yes, I have a question, a little question. Is it possible that there exists another reason why the spectrum could be curved? I mean, another reason behind or different from the cooling time?
Well, I mean, you could initially have an electron distribution which was curved. Right? All this is really telling you is that the distribution of electrons falls off at high energies. That's all it's saying. And you could either intrinsically have that, or it could be from cooling.
Okay. So for example, because of, I don't know, synchrotron H emission could be different, the spectrum?
Synchrotron H? What is the synchrotron age? So by that you mean how long ago it was accelerated?
I was listening about the synchrotron age. That is that I remember that means some population of electrons don't survive too much. I don't know if it's related to
Yeah.
the cooling time or not.
It's exactly related to the cooling time.
Ah, okay.
Yeah.
Okay.
So basically, the age is this, right? So if you have some number of photons, right, this cooling time, you can just calculate it based on this energy and this magnetic field, right? And so for something that has close to the speed of light, and even you could have this magnetic field be the Milky Way magnetic field, 10 to the minus 5 Gauss. And the speed, you could just estimate how long it will take to decay based on emission of synchrotron.
Okay, thank you.
Professor, last class,
Sweet.
you asked us if we would like to change the test from Wednesday to Friday.
Yes.
And
I
Tila
forgot-
actually remind us yesterday, and everyone, we talked about it, and everyone was fine with moving into Friday. I'm not sure if anyone said something, so talk now, please. If I'm
Yeah,
wrong,
I forgot to make a poll. I was going to make a poll and
Okay.
have people do it, but yeah, you could probably just send me an email with your choice, and I can see. But then the issue, I guess, what I should do then also is do a doodle poll to see what times people are available, just to confirm that everyone has Friday off. I'm not entirely sure that's true. So yeah, let me put that on my notes to do that. Okay. So yeah, I'll send out a poll with what I can do is put some times on Friday and the original time on Wednesday. And so if you want to vote for it, you can. But yeah, yeah. Okay. Is it? Yep. Thanks for reminding me. Right, your homeworks are due. I've gotten about half of them so far. I need to send out a new homework. It's going to be the last one before your test. Yeah. And Priscilla has promised me she will be sending them soon for PS1 and PS2. Probably what I'm going to do is just give you the pautas for everything, and you won't have the final grades because she's being a bit slow. But yeah, you can at least compare them, right? I don't guarantee that my pautas are mistake-free, but they should be pretty good. Okay. Yeah, probably she had promised PS1 and 2, problem set 1 and 2 today. We'll see if that happens, but yeah, probably I will just send Pauta 1 through 4 in the next couple of days, and then Pauta 5. Actually, I can send Pauta 5 at the same time, yeah, and then Pauta 6 will be a couple of days before the test. Okay. All right. Bye, everyone.
Bye.
Bye.
Bye bye. Thank you.